In this video, we will discuss the basics of writing rate laws, understanding what rate laws tell us, and solving questions that have some math in it. You will need a calculator to follow along with this video. Okay, so a rate law is generally in this format where it says rate, and rate we've talked about. Rate will be in units of molarity per second. Rate will equal some constant k, and that's a little k, not an equilibrium constant k. And then one of your reactants, so we've got A here and another reactant B here. And notice that they are not to the power of their coefficient, they are to some other powers. And these are called orders. And then K, its units are dependent on the orders that we have. Okay, and so we'll go through how to solve that. And there I've got a quick trick on how to kind of do the units of K without thinking too much about it. We have talked though about that how K is a rate constant, and it's only for a given temperature. So if we change the temperature, we also change the rate constant. And if we increase the temperature, what does that do to the rate? Well, that means that the rate increases. And if we notice here in our rate law, and I'm going to erase some things here, if I need to increase my rate and I only change temperature, well, A doesn't have temperature in it, that's just a molarity, and B doesn't have temperature in it because that's just a molarity. So what that means is that K must also change, and so if my rate increases, K also increases. If I decrease my temperature, my rate will decrease, my particles will have less energy, and so they're less likely to react. K will also decrease here. Okay, so the order of a reaction has to be determined experimentally. We need experimental data. And if I wanted to know the overall order of a reaction, what I would do is I would just add up my order. So I've got an order there, order 1 with respect to A, and B has an order of 2. And so if I wanted to know my overall order, I just add them together, and my overall order would be 3. Just if you wanted to know, you can have decimal orders. We're not going to see that in AP Chemistry, though. So I say don't be thrown if you see something like that. Just trust your math, but I do not anticipate seeing that at all in this unit. So what I'm going to do is I'm going to show you how we figure out how the rate changes if we double a concentration of A or of B, or if we half a concentration, because it may seem intuitive that if we double the molarity, we should also double the rate of a reaction. And that's true sometimes, but it's not always true because it depends on the order. So what I have here is I've gone through and I've just said that the order of A is 1 and the order of B is 2. So A is first order, B is second order, and the overall order is 3. So what I'm going to do is I'm going to say that my old rate, I'm going to just use some easy numbers, 2 and 2. And what the question says is, what happens to our rate? By what factor does it change if we double A? And so if we double A is now going to go to 4, and B is going to stay constant at 2. And I'm going to do the math here. I'm not worried about the specific rates. I'm just worried about how does it change? By what factor do they change? So if I divide these two, k divided by k, that will drop out because k divided by k will be 1. The only thing that changes the rate constant is temperature, and I have no indication to think that we've changed the temperature. And 2 squared divided by 2 squared, those are actually the same, and so those will cancel. And so what I'm left with is I'm left with 4 divided by 2, and so that is 2, and then they're to the first power. So what I am given is that my rate, let me write it a different way, my rate will be 4 divided by 2, which is equal to 2, so my rate has doubled. My rate doubles in this case. Okay, and that's just because we doubled the concentration of A. But let's see if things are different if I keep A the same and I double B. So B is a little bit different because B is to the second power, or it is second order. So I'm going to go ahead and just say my initial concentrations are 2 molar, and that I'm doubling the concentration of B. And so what I'll do is I'll say A stays the same at 2, and B goes to 4. Now I can see what drops out. My K's will drop out, and my A's drop out as well. And so what I'm left with is 4 squared. 4 squared is 16. And then 2 squared will be 4. And so what I'm left with is that my rate has actually quadrupled. Okay, now let's talk about what happens if we half the concentration of A. So everything initially was 2. I'm going to half A, and then I'm going to see what drops out. B stays the same. My K's drop out, and my B's drop out. And so what I'm left with is 1/2. And so my rate here has halved. And so what we're seeing is that if something is to the first power, or if it's first order, then if I double that something, the rate will double. And if I half that something, the rate will half. And that's because it's first order. The math is very easy for us. But we're going to see here that if something's to the second power and we want to half the concentration, that we're not going to just get half of the rate. We're actually going to get just a quarter of the rate left. So let's go through and do that math. We start out with 2, and then A stays the same, and B goes to 1. And so I can cross out what cancels. K cancels, and A cancels. And so I'm left with 1/2 squared. And that is equal to 1/4. And so my rate is now 1/4 of what it was. Okay, the thing that's important here to always recognize is that kinetic information must be determined experimentally. We can, I guess, predict what happens, but we'll have no idea unless we measure it in lab. That's very important to know. AP is very common for throwing a multiple choice question out there that kind of talks about that. And here is how we can get the rate constant units. So the rate constant is K, and so if I have rate equals K, and I'm just going to be simple here and just say A to the first, B to the first. My rate is always in molarity per second, and A will always be in molarity, and B will always be in molarity. And so what happens with K is K's units change, because if I have something that has molarity times molarity and I need to solve for molarity per second, K will give me the appropriate units to do that. But here is a shortcut that what I want to do is I want to add up my exponents. So if I notice here, third order for my reaction is -2 -1. Molarity -2, and then seconds -1. And so notice that 2 plus 1 is equal to 3. If I have second order, I have -1 and -1, and so that will be 1 plus 1 equals 2. And then if I just have first order, that would just be seconds -1, and so that would be 1 equals 1. And then zero order is a little bit different. You can think of molarities to the first power and that they're opposites, and so they cancel to be 0. And you can memorize that. That's great, but it's kind of nice to have a little trick. That way, if you have overall, let's say, 15th order, I don't want to think about the math of how to get all my units to cancel. What I can say is that it's going to be molarity to the -14, and then seconds to the -1. Hopefully you have caught on that no matter what, we will have seconds to the -1, and that's the max that it could be, seconds just to the -1. And the reason that is that I have to get per second, and neither of my molarities are going to give me that. And so I must have in my K, I'll have some number of molarities to some power, but I'll always have seconds to the -1.